welcome to this morning session. It is a pleasure to introduce Professor Luigi Accardi from Università di Roma Tor Vergata. He will speak about the three new principles in non-equilibrium in statistical mechanics and their mutual relationships. Please.
So, thank you very much. I'm very glad to be again in Mexico City. And since we have, and in particular in this occasion, to have the possibility of a dialogue between mathematicians and physicists, which we are trying to do since many, many decades. And I had the pleasure and the honor to know personally Leopoldo García-Colín, because I gave a talk in 2008 in his seminar in Università Autonoma Metropolitana. This was an occasion of a lot of discussion. So this conference is an occasion for me to renew this contact, even if indirectly. I will speak of three new principles in non-equilibrium statistical mechanics. But since these new principles were not generated by a physical idea, they were generated by some mathematical developments, so I want to briefly recall you what kind of development. This development has to do with some theory which we call stochastic limit, and let me try to frame this theory with some kind of philosophical remarks, you see, which seems to me appropriate to evidentiate, emphasize what is the goal of stochastic limit of quantum theory. So at the beginning of the century, there was this view of physics which was rather naive, a totally reductionistic point of view in which there are fundamental laws and all the rest is work for chemistry, for engineers, and so on. But now, after 1 century, we understand that, the situation is much more complex. And I want to refer to a very famous article by Philip Anderson, who at that time, when he wrote this article, he didn't yet receive the Nobel Prize. But what he was saying was very deep and very illuminating to describe the present situation, not only in physics, but in all physical sciences. So, as you see, he was saying that this idea that at each level of complexity, there are new properties that arise. And the traditional program of reductionism is by far realized. You see, he brings some examples in disciplines which are very high in the hierarchy, but I invite you to reflect on the fact that we have not a really deductive theory of crystals. So even at a much lower level of complexity, the really deductive program has not really been implemented. Okay, so what is the lesson that we can extract from this message of Anderson? The message has to do with scales, that there are new phenomena at each physical scales, and the physical scales are very many. Now, typically, but what happens? Okay, so the physical scales are very many, and any attempt to privilege one scale with respect to the other is harmful for human knowledge. So let me give you some idea of what was how to frame the stochastic limit of quantum theory. So we postulate that the basic laws of physics are true, and they involve any scale. But just because they involve any scale, to read the physics of a certain given scale can be completely impossible. And I think the first people to understand this was in the 60s, when they began to study quantum optics. And I remember a series of arena lectures by Gordon, who was saying that after all, in the dipole approximation, the quantum optics equations are linear. So in some sense, they are completely trivial. But the real point is to read the physics in this equation, is not to write the equations. And this is the point with the reductioning problem, okay? So you see that in the history of science, we have to, it's not true that once a theory overcomes another, it includes it. It is true that only in an asymptotic sense. And you have a lot of known examples. I will not insist on them because they are very well known. In what sense there is an asymptotic agreement, but not an inclusion. Moreover, I want to point out a difference between this kind of asymptotic agreement. You see, in the first three items, special relativity, general relativity, and quantum theory, we have a special case in which a new theory asymptotically agrees with an old one. But in classical statistical mechanics, as well as in quantum, we have a different direction. We have an old theory that in a limit, typically the limit of infinitely many particles, will asymptotically generate a new theory and new collective phenomena arise. So this allows me to come to the point of stochastic limit. Stochastic limit belongs to the second category. That is, what we do is we also isolate a very special scale, and you will see in a moment what scale is this and what physically means. And we start from the basic laws of physics, the basic Hamiltonians, the QED Hamiltonian, spin boson, standard physical Hamiltonian. And then we introduce the scale. The scale is introduced by combining the two basic asymptotic regimes of quantum physics, perturbation theory and scattering theory. Perturbation theory has to do with small parameters. We will see many examples, not only coupling constant. And scattering theory has to do with long time. So what we do is we try to extract the cumulative effect of very weak interaction on very, very long times. Okay? So we have two scalings. Lambda will go to 0, tau will go to infinity, but there is a constraint. There is an old story on this constraint. I have no time to say why exactly square, but it's important that if you take either 2 plus epsilon or 2 minus epsilon, the limit either is identically 0 or is infinity, it doesn't exist. So the power 2 on the small parameter is exactly the only possible choice. There are no other ones. Okay, so since there is this constraint, the two rescaling are equivalent to a single one. What is the physical meaning of the rescaling? In the rescaling, we have rescaling the time t by the inverse of the small parameter. So time t will represent the slow degrees of freedom, the time unit in the small degrees of freedom. And the t over lambda square, which is enormously larger, will, because don't forget that lambda will go to infinity, will represent the time scale in the fast degrees of freedom. Okay? So what is the intuitive picture? Is that if I look from the clock of the slow system, the fast system, I will have the impression that the fast system is a quantum noise. The stochastic limit makes the mathematics of this intuition. It is a theorem that this is true. More precisely, what happens? The fast degrees of freedom of the system will converge to a delta correlated quantum Gaussian field. Quantum Gaussian field is just typically a non-relativistic field. We are in non-relativistic setting. So such Gaussian fields, which are delta correlated in times, in mathematics are called white noise, and in physics are standard boson field. There is the Fermi analog, but we will not discuss in this talk. So, in some part of the literature where another scaling is used, so-called 1/n scaling, the term master field also is very used. So what is the picture that emerges from the stochastic limit of quantum theory? The first degrees of freedom become quantum noise. And, okay, I repeated it twice. The Schrödinger equation becomes a white noise Hamiltonian equation. This is a very singular equation. It's an equation in which the right-hand side are not usual operators, they are so-called operator value distribution. A typical example is, for example, the delta potential. This is a second quantization of the white noise is essentially the second quantization of the delta potential. Okay, and what is interesting is that the Heisenberg equation also goes to a white noise Heisenberg evolution, again singular, but a kind of singularity which is familiar in physics, because in quantum field theory, the equations of quantum field theory are equations with operator value distribution. So from this point of view, there is nothing new. But the point is that these equations, in this equation, the order of time plays an important role. It is an important fact that they are evolution equations. Why it is important? Because there is a theorem which is mathematically probably the main result of the theory, that a white noise singular Hamiltonian equation is equivalent to a quantum stochastic differential equation. Quantum stochastic differential equations are a generalization of usual stochastic differential equation. And stochastic differential equations, as you know very well, are used to describe in classical and in quantum physics to describe dissipation and transport phenomena. So this explains the philosophical meaning of the stochastic limit. The stochastic limit is the mathematical theory of dissipative and transport phenomena in quantum theory. I will not discuss this, but there is a book that was published now rather long ago where these kind of things are described in more detail and illustrated with a lot of concrete physical model, which start from the simplest one, which is the standard, for example, spin boson Hamiltonian, we call it the level 1, and ends up with the quantum electrodynamics without dipole approximation. To our knowledge, there is no result which is precise in quantum in QED without dipole approximation, and there very deep new phenomena appear. But I will not have the time in my talk to discuss this level 3. I will stick to. So what is, let me try to describe very intuitively what are the actors in the stochastic limit. We are in the so-called open system framework. So we have a system which intuitively represents the slow degrees of freedom, and an environment. Typically, it will be a field, or in low density limit, a low density Bose or Fermi gas, okay, called reservoir, okay? And intuitively, the system we should think as a small system. So typically, it has discrete spectrum, but we have a lot of results. This is the famous level 3, in which they have continuous. In my talk, I only discuss discrete spectrum for the system. And environment, in some sense, is large. I give a tentative definition, but I must confess that a precise definition of what is the difference between a system and an environment is, I consider, still an open problem. As my tentative definition, I say that an environment is an Hamiltonian system which has two properties. First, it must have infinitely many degrees of freedom. Second, it must have integrable pair correlation. Why this apparently very technical point? Well, if you do the calculation, you see that from this pair correlation is you obtain exactly the integral of the pair time correlation gives you the susceptivity, the generalized susceptivity, which are the fundamental physical constants, which are the transport coefficients. Okay, now, the system space I will denote HS, and the one particle environment space will be typically L2 over D with typically D greater or equal than 3, because for D equal 1 or 2, the integrability of pair correlation for Hamiltonian system is more a problem. Okay? Then the algebra, typically we will consider bounded observable, but in physics we also use position and momentum, which are not bounded, but they are affiliated to this algebra of operators. And for the quantum, the environment part, we will have not a Hilbert space, but an algebra, because the Hilbert space is determined by a further choice that we will discuss later, which is the state of the environment. The state determines the representation, and therefore it determines the Hilbert space. So typically, we will only discuss a boson field with standard boson commutation relation, and these are the commutation relation in test function language. Now, as I said, Hamiltonian is a discrete spectrum. Hamiltonian has discrete spectrum, and the one particle environment Hamiltonian is given by a dispersion function, which is very much used everywhere in physics. Typically, omega k is modulus of k for non-relativistic QED, and it is the kinetic energy of the single particle, of the one particle of the gas, for the free Bose gas. So this are the two, but in solid states there are many, many more examples of dispersion functions. The state, typically, we will take a particular class of states, which are product states. There are, at the moment, no result for initial states, which are not of this type in the stochastic limit, and to my knowledge in any other application in physics. So the state of the environment is determined by the analog of the moments of a classical probability. These are non-commutative moments, because the field operators don't commute, but they are like the mixed moment, and they have, in physics, many names, like correlators, or a Whiteman function in quantum field theory, or Schwinger function in Euclidean field theory. When the state, as I said before, will determine the cyclic representation of the field. In physics, to my knowledge, at the moment, there exists only two classes of states of environment, that is of infinite extended system, that are explicitly known. And this class is the class of Gaussian state. Gaussian states are characterized by the fact that the moments of any order, so the correlators, are uniquely determined by the pair correlators. And you have various possibilities according to the covariance. Typically, you call gauge invariant the states which have an off-diagonal covariance, and typically this will be the non-Fock term, and this is the Fock term. This, we will consider the special case in which we are in momentum representation, and the non-Fock term is given by a density function, which is the density of quanta at momentum k, and the plus and minus sign is due to the commutation relation, and therefore is plus for boson and minus for Fermi. So according to the choice, even in the diagonal case, there is a lot of possibilities, and we will see that the physical picture corresponding to different choices of densities will change drastically. For example, the most famous example is the difference between the Fock state, which is the one most used in the literature, and the finite temperature equilibrium states. With you see, there is this Z is the fugacity, which is the typically is the exponential times the chemical potential, and it will play an important role in the low density limit, but we will not discuss low density here. So the interaction Hamiltonian have two types. They distinguish two characteristic types of Hamiltonian. In one, you have the coupling constant multiplies the interaction. So we are in so-called weak coupling regime. In the other one, we have a strong coupling because the coupling constant does not multiply the Hamiltonian, but it is implicit indirectly in the representation of the field, because we are in equilibrium at a certain, with a certain state which has this form that I mentioned to you. This state, you see, this is the equilibrium state with Z, and Z will be the lambda, the small parameter, because you can prove very easily that asymptotically, when Z goes to 0, the Z becomes proportional to the density of quanta, and so it is interpreted asymptotically as a density. So we have these two regimes. They lived completely different. The second regime leads to Boltzmann type equation, but as I said, I will not discuss. I only discuss the first one. But they have in common the scheme. The common scheme is this. You first introduce the wave operator at fixed time t. And the wave operator is known to, and the corresponding Heisenberg evolution. The wave operator is known to satisfy so-called Schrödinger equation in interaction representation. So after the rescaling, you have the rescaling, and you have the rescaled equation. And you see from the fact that the t is rescaled like 1 over lambda square, that the limit should be something very singular. This is in some sense the premise of the appearance of the delta function, this kind of rescaling here. Okay? Now, what are the results of stochastic limit? As I said, when lambda goes to 0, the field will correspond to a new field for k and k primes always represent the momentum of the field, but now there is also time. It's a momentum time field, and the covariance will be given by this formula. Epsilon and epsilon prime means the operator or the adjoint of the operator. So this is the typical covariance. Okay, now the Schrödinger equation will have a limit. The solution of the Schrödinger evolution has a limit, which is a white noise Hamiltonian. That is, I will not write at the moment, maybe later you will see what does it mean, white noise. Is that this, like the old Hamiltonian was a function of the fields, the new Hamiltonian is a function of the singular fields, the field, the so-called white noise. And you have the analog for the Langevin equation. Langevin equation is nothing but the Heisenberg equation in its stochastic limit. Okay? What will be new the new developments I anticipate is that, well, let me go on and then I will explain better. So there is a connection with the stochastic analysis, and I already told to you before. This is given by the theorem that establishes the equivalence between white noise Hamiltonian equation and stochastic differential equation, so the theory of dissipation and transport. Now, how the irreversibility comes out in this scheme, and this brings back to the old papers by Ivanove, who was one of the pioneers together with Bogolyubov in this field of stochastic limit. So you have the Langevin equation and the Langevin evolution, which is nothing but the Heisenberg evolution. This is before the limit. But before, when lambda goes to 0, this converges to the Langevin evolution, to white noise evolution. If you trace out, and here it comes, if you trace out the environment degrees of freedom, you obtain what is called a one-parameter family of maps, which have a very special property. For those who listened to the talk by Franco Fagnola yesterday, this is a typical example of completely positive evolution. That is why completely positive evolution are natural in physics, because they come out by tracing out the environment from a standard Heisenberg evolution. Then they must be necessarily completely positive. It's not an arbitrariness of mathematics. It's simply inside the physics. What is important is now that we have an evolution equation, which is now a Markov semigroup. Markov semigroup, in addition to positivity, it preserves identity. And this you can see from here immediately, that this is, when you put the identity here, you get identity. Now, like any theory in physics and in any science, also in mathematics, the stochastic limit comes at the end of a very, very long historical development. This, as I mentioned, began with papers by von Neumann with the so-called random phase approximation, and then Pauli with the master equation, and then Bogolyubov, and then the first really concrete and important results are due to Van Hove. That is why one often speaks of the Van Hove limit. And there are many names, many techniques in physics that have been used to achieve similar results, but they are approximation. What is the difference between Born approximation, Van Hove limit, Wick-Kapping limit, many limit, and stochastic limit? The big difference that qualify the different name is that all this approach only obtain the reduced dynamics, only obtain the semigroup. So they lose completely the information on the environment. But you will see that this information on the environment will be precious if we want to deal with non-equilibria, because in non-equilibria we will have to deal with the currents, and the currents are currents of quanta, so they have to do with the field and not with the system interacting with the field. Okay? So now there are many things that in the book that I mentioned, we do a lot of examples of things that can be done with the stochastic limit, but not with the semigroup. But I want to give you one example. As I said, I want to discuss this new development concerning non-equilibrium. So in non-equilibrium, as we said before, there is this operator which represents the density of quanta in the momentum k, okay? And we look now at the evolution. We know the expectation, the mean value at time 0. We are in an equilibrium state, and after stochastic limit, we are. What is new in the stochastic limit is that we can give a meaning to this operator, even if the white noise lives in a space which is not the same Hilbert space as the initial degrees of freedom of the environment, but we can give a meaning to this evolution in the limit. So we can calculate the average for the limit state, and therefore we can take the derivative of this average, being the derivative of a time-dependent density, it is a current. In this case, it is a current of quanta. So after that, we use some technical points which I don't discuss here, and you explicitly calculate this derivative, and you find that now you see the term microcurrent. You see, this is a current corresponding to momentum k, okay? And this current, epsilon n, are the energy level of the discrete system. Let us say atom, to fix the idea, okay? These are the energy levels, and the difference of the energy levels are called so-called Bohr frequencies. So you have a delta function which says that the whole field is, in some sense, foliated in a lot of surfaces depending on the function omega, which in some sense resonate with the Bohr frequency. And this is a sum over all. Pay attention that we are only in the stochastic limit for the currents, only the up-down transition counts, Of course, you can also have the down-up from the lower level to the upper level transition. But this will not give contribution to the current. Okay? So we see that the global current at momentum k is a sum of microcurrents. Each microcurrent is associated to a given Bohr frequency, that is, to a given transition in the atom. Exactly, it takes those momenta of the field which resonate in energy with this transition. Now, we obtain, just one moment, what I want to point out your attention is that this evolution of the microcurrent, which is an observable of the field, depends on this rho, which is the density matrix of the small system, evolved according to this unitary evolution that we obtained in the limit. So the current this is physically obvious, because the currents that are obtained by the field or given by the field, they come from the transitions in the atom, or the converse process in which the atom acquires some quanta coming from the field. So it is natural that the population density of the atom in some sense determines the field. But what is really interesting to notice in this equation, suppose that rho is a stationary measure for the semigroup, the Markov semigroup that we have discussed before. Then, you see, if rho is stationary, it doesn't depend on t. And so the microcurrents are constant. Okay? There is a very particular constant, which is important in physics, which is 0. And in fact, 0, as we will see in a moment, exactly characterize so-called detail balance or equilibrium situation. So you see, from this rather simple calculation, we deduce some, which is a very natural generalization of the detailed balance principle. You see? Now, here I am writing the same thing, but I am integrating, and in fact, the integration is not over all the momentum space, but only on the resonant surface, which I call surface. It could be some. What it is, it depends on the function omega. But okay. So the explicit form is important because it shows how the balance of the microcurrents depends on everything in the interaction. If you remember, N defines the initial state of the field, Nk, capital Nk. G is the interaction, is a form factor in the interaction. And the transport coefficients are explicit. We can calculate explicitly. Okay? This is one of the main results of the theory, because the physics is there. Now, so as I said before, when you have the stationary state of the field, then the microcurrent are reduced to this constant. And when the constant is 0, we arrive in a moment, we will show that we get so-called detailed balance. And so we, with Imafuku, we introduced this long ago when we first studied this problem, we called this the dynamical detail balance, because it's a generalization of detail balance, which is very, 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 in some sense, trivial. You simply say that the microcurrents, instead of being 0, are constant. But each constant, of course, can depend on the omega, on the Bohr frequency. Okay? Again, the transport coefficient, a little bit more detail, but I have no time to discuss how to. Imaginary part gives a contribution to the shift. to the energy shift, which is a generalization of the famous Lamb shift. But this is a universal phenomenon. It's true for all. In the stochastic limit we see, and the shift is not necessary. It can be red or blue. It depends very much on the interaction, what kind of shift we have. Okay, now let us go to detail balance. As I said, detail balance is characterized by the fact that all the microcurrents are identically equal to 0. But if they are equal to 0, it means that this difference is 0, and therefore, supposing that everything is strictly positive, we obtain that this quotient must have this form. So we come to the importance of having the explicit form of these constants. Because since in the stochastic limit you have the explicit form of this constant, which is this integral, you can calculate this integral, this transport coefficient, and you see it becomes a universal factor which does not depend on the interaction. The quotient, well, the constant depends on the interaction, but you see here we are interested in the quotient, and the constant is the same. So the particular case is eliminated in the quotient, and you get a universal factor. And in fact, this universal factor is a generalization of the very famous, this is a generalization for arbitrary interactions of the very famous Einstein formula for radiation theory, which is given when, you remember, this is just the average number of quanta in the density, corresponding to the transition from epsilon m to epsilon n. Epsilon n is the smaller energy, and we see that we obtain this, which is typical. You see, this is the Einstein formula is a very special case. Why? Because Einstein formula is an equilibrium relation. The radiation formula postulates that this n has a very special form. Let us see what is the form of n which gives equilibrium. So, you see, if you have this quotient here, the quotient of the density matrix is equal to the quotient of these coefficients, then necessarily this, you can always write this object because it's a strictly positive number, and you write as the exponential of some positive number. Notice that this is beta that appears canonically here is not the inverse temperature, because it's a function of omega, nonlinear function, because the left-hand side is a nonlinear function of omega in general, okay? Now, suppose that the detail balance condition, not the dynamical detail balance, the standard detail balance, which means this, that this quotient is equal to this, is satisfied, and then you simply have, by elementary calculation, multiplying and dividing by rho k, that this function of beta essentially must be additive. And the only additive functions are the affine functions, or in this case even linear functions. So the equilibrium condition exactly characterizes the situations in which this beta, which is in general a function of omega, is a linear function of omega. When you find the standard formula, the Einstein formula, which this is the Planck factor. Okay? But this is, I insist, the equilibrium. So, since we have the formula for the microcurrents, which is general and allows to go beyond equilibrium, it's very natural to say what will be the radiation formula in the non-equilibrium situation. And for this, we have to study the stationary states for the Markov, for the semigroup, the Markov semigroup, the differential form of the Markov evolution is called the master equation in the literature, and is a quantum generalization of the standard diffusion equations. Now, how much time? 10 or 15? Good. So now we are approaching what is the challenge of this talk. How to use this information on the microcurrents to extract non-trivial information on non-equilibrium phenomena. So we use the following fact, which is rather well known. Let ρ be the stationary measure for the reduced evolution of the reduced evolution of the system, which is this one. I denote PT, and the generator is L. So now, in the case of equilibrium situation, Frigerio, Gorini, Verri, and Kostakowski also, I forgot to write here, they gave a very interesting characterization of the equilibrium measures in terms of the following properties. That if I consider the generator of the Markov semigroup in the equilibrium measure, then important phenomena happens. This adjoint, which always exists as abstract operator, but very rarely is again a Markov generator. So it's not like in the classical probability that the adjoint of a Markov generator is always a Markov generator. Here, the adjoint may exist, but is not. In equilibrium state, it exists. In non-equilibrium, in equilibrium state, it exists. Moreover, the fact that the adjoint Markov generator differs from the standard generator by a derivation, that is the commutator with a certain self-adjoint operator, which is not, this is a system operator, but is not necessarily the Hamiltonian of the system from which we began. It is, this is the Hamiltonian shifted by the generalization of the Lamb shift that I mentioned to you before. This generalization is a new additive Hamiltonian to the system that still is a function of the old one, so commutes. And therefore, it is this, this relation is very special, you see. It says that there is, and according to Gorini and Frigerio, this characterize the equilibrium situation. Now, let us use again the peculiarity of the stochastic limit to try to obtain a similar relation, but without using the equilibrium, because in non-equilibrium we don't know nothing on the invariant distribution for the system. So what we can do, however, the stochastic limit technique can be applied both forward in time, but also backward in time, because standard unitary Heisenberg evolution is reversible. So we can apply, and we can calculate the forward flow and the backward flow in the stochastic limit. Now, again, we can calculate the forward master equation and the forward generator, and as you see there is a derivation here, delta, which is the H operator I wrote before. And then there is the dissipative part. This is the dissipative part, which is typical of the quantum Markov semigroup. And the same calculation for the backward equation gives you exactly the same situation that we find in the Gorini, Frigerio, Verri, and Kostakowski characterization of the equilibrium state, only that we are not not taking any expectation. And intuitively, this is obvious, because if you have an Hamiltonian evolution, the Hamiltonian is reversible. So if you take the limit in the backward direction of time, you naturally expect the minus sign in the Schrödinger equation, because it corresponds to the time reversal. Okay? So we see that the forward semi-generator minus the backward generator satisfy the same relation that, according to Gorini and Frigerio, characterize equilibrium. But what is the difference? That here we have not the adjoint with respect to the stationary state. We have just the backward generator in the sense of stochastic limit. So let us see what will be the difference if we compute the adjoint now with respect to the invariant state. So now we have a in general non-equilibrium situation. The semigroup is the one associated to the non-equilibrium state, and ρ is invariant state. Now we calculate the difference between the generator and this ρ adjoint. So the adjoint for the scalar product given by the trace. Okay. So we calculate this difference. You see, this difference is easily calculated, and you find that it is driven by a very special operator that we call the current operator. And in the equilibrium situation, the current operator is precisely zero. Why we call the current operator? Because we have the explicit formula of both generators. And we can calculate explicitly this difference. And we can prove that this difference is exactly expressed in terms of the microcurrents that we deduced as elements of the field, as observables of the field. So, generic case is a very special class of system. It's a property of the small system. Roughly speaking, a non-degenerate Hamiltonian means, I have this, thank you. Roughly speaking, a non-degenerate Hamiltonian means that the spectrum of the Hamiltonian is non-degenerate. A generic Hamiltonian means that the spectrum of the Liouvillean associated to that Hamiltonian is non-degenerate, and it is a much more stringent condition. Under this condition, the semigroup and the generators have a very, very nice interpretation in terms of the transition probabilities of observable. Remember, X and Y are observables of the system. And epsilon L, epsilon M are the energy level of the atom before the stochastic limit, okay? And so you recognize that in the generic case, you find again exactly the same expression that we found when we calculated the microcurrents of the field, but as intrinsic property of the field. Not. Here we are doing a system calculation. So this is the real interplay of the interaction. So the problem is that the physics of non-equilibrium reflects very clearly in this kind of generators, because the coefficients that define, you see, you have the operator L. You have the operator L, and we have proved that the difference between the ρ adjoint of L and L is microcurrent operator corresponding exactly to that ρ, for which we define the adjoint. Okay, so, I want to arrive to what is now our research that we are doing since several years with Roberto Quesada and Franco Fagnola, namely, now that we have this non-equilibrium situation, let us sum up how we arrived to this non-equilibrium state. We start from a Gaussian state, which is in general non-equilibrium of the field. And this Gaussian state is such that after the stochastic limit, it drives the small system. This is typical in thermodynamics, but this is true for every interaction. It drives to a certain state which remembers the state of the big system, the environment. Okay? So the reduced evolution, which is an evolution of the observable of the small system, is a Markov evolution. So it is defined by a Markov generator that we define, we call L. This Markov generator is a very special structure because it comes from a precise interaction, a nonlinear interaction. So it depends on all the Bohr frequencies of the atom, but the strictly positive ones, as I said before. They contribute to the dissipation. It depends on the transport coefficient. And the transport coefficient depends on everything. They depend on the omega function defining the energy density of the field. They depend on the state of the field. They depend on temperature, the nonlinear temperature function that we introduced. Okay, so you see that this semigroup has a very, very special form. And in this very special form, I will here neglect, there is an Hamiltonian term, typically is not so important, but it physically, of course, is very important. And the generalization of the Lamb shift, so it is important. But these are the dissipative terms. So this is the non-Fock, and this is the Fock contribution, okay? And this is difficult, yeah. Okay, this can give more insight. If you look at the coefficients, the operators that appear in the generator of the semigroup, you really see what a very important role that we are discovering, and because it has very non-trivial physical implications, namely the role of degeneracy. Remember, in the generic case, these projections are rank 1, and this is simply a transition probability, a matrix element of this D into these two energy states multiplied by the flip operator corresponding to these two states. But in the more general situation, when you have degeneracy, what does it mean? It means that you can realize the difference epsilon n minus epsilon n equal omega with many pairs epsilon n, epsilon n. Then you have a more complex situation, and mathematically this is reflected by an important property that we do not still completely understand, because we have not a characterization of the group of the generators which enjoy this property. What is this important property? I have shown to you that the difference of the two generators is exactly the current operator, okay? Now, in the generic case, this current operator, this adjoint is still a Markov generator, and the current operator is a very special structure, so-called completely bounded map. Mathematics is a very special, important property. And but the important point is that the L star rho is still a generator. Okay, when there is degeneracy, this is not a Markov generator usually. But at this moment, we cannot characterize the intermediate level. Surely there are some Markov generators which are between the generic case in which the rho adjoint is still a generator and the non-generic case in which it is not. Why this is important? Because this phenomena is again driven by the microcurrents. So it means that objectively this really corresponds to different physical situations. It's not a mathematical property abstractly given. Okay. So, okay, this is what we call a Markov generator of weak coupling limit type. You see, it has this very special structure that you find in this line. It is a Hamiltonian part plus there is a common transport coefficient which depends only on the Bohr frequency of the transition, and this corresponds to the adjoint process. Typically, these are down transition and up transitions. And so you see that this kind of particles, this kind of generators are very interesting. Why? Because, as you see, the appearance of the transport coefficient shows that this sum, to imagine that the Bohr frequencies are pairs of frequencies. So you can imagine a lattice in which you have on both axes the discrete energy level of the atoms and all the pairs. But if you take out those which give 0 to this d omega, so typically these are transition elements of the interaction operator. So it's an interaction of very special type. Okay. Okay. So, since time is running very much, let me try to make a conceptual summary of what I said. Okay, so we started from a non-equilibrium state of the field. We applied the stochastic limit technique, and we arrived to a certain special class of Markov semigroup. And now we try to solve the converse problem. Which Markov semigroup come from the stochastic limit of interactions with the non-equilibrium field? There is a point that I announced in my abstract, which is rather interesting. We have seen that the main difference between equilibrium and non-equilibrium, let me recall you this, the main difference is in this function beta, which is in general okay. This function, you see, we use this, the transport coefficient, to define what we call the inverse temperature function. And then we prove that only in equilibrium this is equivalent to the fact that the inverse temperature function is linear. So if the states for which this inverse temperature function is non-linear function, we call states of local equilibrium. And now you know very well that the global equilibrium is characterized by the Gibbs principle. And the theorem is that we have exactly the same Gibbs principle for the local equilibrium. And the Gibbs principle, the Gibbs form of the density, invariant density matrix, is equivalent to the famous Kuba-Martin-Schwinger condition. And we can also formulate a nonlinear Kuba-Martin-Schwinger condition, and we prove that the two give the same result, the same structure of states. So you see, we started from a very particular class of model, and we individuated a certain property. And what is this property? From the physical point of view, it differs from the old proposal by famous physicist Zubarev. Zubarev was proposing to consider non-equilibrium states with position-dependent temperature, which is obviously very natural, because in a room I can have different temperatures in different places. So it's very natural for physics. But the states that Zubarev proposed cannot be stationary states. Why? Because if the temperature depends on position, the function of position should be in the commutant of the Hamiltonian. And this happens practically for no reasonable Hamiltonian. But in our case, we put Hamiltonian in momentum representation, which is the multiplication by omega k. And this is a function of omega k. So we have a lot of examples of stationary non-equilibrium states, which is the simplest class of states after equilibrium. And I think, we have a lot of physical application in different fields, but I have no time to tell you what are these applications, but there are, you can look in the book and in the papers after the book. But I hope that the main message of this new kind of local equilibrium state has reached enough of you. Thank you very much for attention.
We have time for some questions or comments. Yes, please.
Yes, there is this very nice paper by Schwinger in '61 about the quantization of the damped harmonic oscillator, or the forced damped harmonic oscillator. And in this case, he doubles the Hilbert space to get a Hamilton function or two Hamilton functions. And one of the Hilbert space, the time is running backward, and the other was forward. So this means some elements you presented here in a strict mathematical sense, Schwinger introduced an example of this damped harmonic oscillator, where he had, so to say, a quantization of a non-equilibrium system, namely the damped harmonic oscillator.
Yes, of course, this state, the Gaussian states which are non-equilibrium, of course, they were very well known since, I would say, the beginning of quantum theory. What is the point of stochastic limit? Is what we call the similarity principle. That is, our state of non-equilibrium is not the state of oscillator. It's the state of the field, of the environment. And then there is this very non-trivial theorem that when you do stochastic limit with a state of the environment, which is non-equilibrium, you get a semigroup. This semigroup will have generically an invariant measure which is non-equilibrium with the same inverse temperature function as the field. This is the non-trivial point, the similarity principle. Of course, the field is our starting point. The field is non-equilibrium, because that was our question. In many years, we began with the Fock state, and we see that the semigroup drives to the ground state of the system. We began, and if we begin with the equilibrium state of the field, the semigroup drives to equilibrium with the same inverse temperature. And so we asked, what happens if we apply a Gaussian but non-equilibrium state? And this is the result.
Yeah, thank you.
Another question? Yes, please.
There are two models in physics that for dissipative systems that are well known. One is the imaginary potential, that is typical in nuclear physics. There is another model that is the imaginary channels, fictitious channels, in which you can take the dissipation in these channels. My question is how these formalisms will fit with these other well-known models of dissipation.
These well-known models were exactly the beginning of the theory of Markov semigroup. Because in physics, in the early times of physics, if you look, for example, the Feynman lecture notes, the usual approach to describe dissipativity and transport was exactly this, to put an imaginary term in the Hamiltonian. a phenomenological imaginary term. What is the problem with this? People discovered soon that with this addition, you get something which typically will be contractive, will go to zero. It doesn't map states into states. So either you normalize, and then you get a very complicated nonlinear equation, like in quantum filtering, or you do the normalization that we do with the stochastic the generators of Markov semigroup. If you look at the structure of generator, there is the anti-commutator, and there is a certain map which is called completely positive map. This map is exactly what reestablishes the normalization. And that if you take a simple point of view with the non-self-adjoint Hamiltonian, you cannot obtain this. You cannot obtain this normalization. So the theory of Markov semigroup is the development of this approach.
I know colleagues who study the problem why the macroscopic world behaves classically. So if taking this example, why the moon does not behave like an electron in the hydrogen atom, and the technique is called, what they call is decoherence, and the approach is exactly the same you use. So we have a system, we have a bar.
How is it called?
They call it decoherence. And it's a very, very, but the idea is just the same. So the idea is you have a system, you have a bars, you have an interaction. At some point, they trace out the bars variables. And then, which means due to this decoherence, which means the moon interacts with everything, with photons, this and that. And in the very end, you end up with a classical equation. Is there any relation to the things you're posing, since the idea is the same?
Well, this is, as I said, no development in science is born for nothing. This is the famous, how to say, the projection method that was used by Zwanzig, by Kubo, by many, many people. What is the problem with that? That if you don't do stochastic limit, when you take the reduced evolution, you don't get a semigroup. Now many people want to study this, but it is a terribly bad. Again, the equation you can write, but you write something on the paper. But if you look at the semigroup, you really see the physics in it. You see the transitions, you see the transport coefficient, how they depend on the Bohr frequencies. You really read the physics in the semigroup. But then you have to go to the stochastic limit.
More questions? Yes, please.
Can you relate your definition for beta with some fluctuation or generalization of fluctuation dissipation theory?
Yes, yes. In the book, there is a full chapter on how this gives you a more general and more complete approach to the standard theorem of fluctuation and dissipation. And in sense, this beta is a kind of nonlinear generalization of fluctuation and dissipation. We have also a nonlinear generalization of the Onsager relations in the same paper. My point is that if I can do myself a question to the physicists present, is I am looking since many years to the possibility of physically realizing this frequency-dependent temperatures. So the intuitive picture that comes if you look at the generator is just as if every Bohr frequency is in equilibrium to a temperature which depends from that Bohr frequency. This seems to be a rather natural situation, and I am convinced that in physics there should be some manifestation of this, because what is natural in mathematics, in some sense, should be natural also in the natural world.
Another question? Well, if we don't have more questions, let's thank the speaker again. There are some posters on the table that are for distribution among the participants, so if you like, you can have one. And thank you.